Let's say that we're unloading rocks from the back of a large truck, and we start to wonder how heavy these rocks are. So during the first 50 rocks, we find that 20 weigh 30 pounds, 5 weigh 50 pounds, 10 weigh 20 pounds, and 15 weigh 5 pounds. So we have a distribution of weights here. Let's draw this out. So here's N, and here's the weight. So there are 20 rocks that weigh 30. There are 5 that weigh 50. There are 10 that weigh 20, and there are 15 that weigh 5. So weights are measured in pounds here. What is the average weight of each rock from our sample of 50? So we could use our average equation and just add up all the weights and divide by how many we have. But we don't really want to do that because that would take forever, right? We have 50 rocks here, and I don't want to take the weight of 30 plus the weight of 30 plus the weight of 30, right? And how many of those do I have? I've got 20 of them. And then do that same thing for the 50s, right? I've got 5 of those. Yeah, this is going to take forever. Eventually, you see that you would have 20 30s, you would have 5 50s, 10 20s, and 15 5s, right? So you can use some algebra to make that a little bit easier on yourself, but we actually already have a name for this, and we give this the expected value. This is the general equation of an average. So this average equation will work if all of these W's are uniform, right? If they all occur once, right? I counted a 30 once and I counted a 30 once. But I can use my expected value if my data is distributed, and that's exactly what we have here, right? I have several 30s and I have several 50s. So let's do the expected value equation. Expected value is a general average, and we get that by summing the weights multiplied by the probability. Oops, that was bad. The probability of that weight occurring. So here the first weight is 30 pounds, and the probability of a 30-pound weight, well, there's 20 of them out of the 50. The next weight is 50 pounds, and there are 5 rocks out of the 50 that weigh that. And we'll do this for all of the different types of rocks. So we have a 20-pound rock, 10 out of the 50 weigh that, and we have a 5-pound rock, and 15 out of the 50 weigh that. So really, you're kind of doing the exact same thing, right? You're taking 30, multiplying by 20, just like you did up here, and then you'll divide by 50 at the very end. So once we do this, we find an expected value or an average weight of 22.5 pounds. So from our sample of 50, the average rock weighs 22.5 pounds. Now, what is the best estimate for the true weight, or rather for the true average weight of all rocks in the truck? Well, that's given to us by the central limit theorem, right? We have a sample of 50 that weighs 22.5 pounds, and let's remind ourselves of what the central limit theorem says. If the weights of rocks are distributed with some average and some standard deviation, then the average weight of the rocks will be normally distributed with the same average and now a standard deviation that's dependent upon your sample size. So if our average weight of the 50 rocks that we sampled was 22.5, then the average weight of the rocks will have, or the average of the average weights of rocks will be 22.5 as well. So from your sample, you had an average of 22.5 pounds. So your best guess at the average weight of all rocks in the truck will be 22.5 pounds.